Hello everyone. Today we are going to be learning about how to make a tangent wrap around a curve, any curve, um, depending on whichever x coordinate is put in place. So, suppose we have a function, a quadratic function, equals to 3x squared minus 5x plus 6, right? So this right here is a quadratic, and what we will do with it is we know that let's just define a point P, right? So we'll define a point P, or let's not call it P. Let's just make it a pair of coordinates. We'll have P and f of P will give us a coordinate that wraps on this curve, a coordinate that lies on this curve, depending on whatever the x value of P is. Now, when P is 0, for example, you can see that it is at 6, which is the y-intercept. Now, we want a tangent that depends upon whatever the x value of P is. So, whatever P is, we want that tangent at P. So, for example, at 0, the tangent will go down like this, right? Somewhere in this direction. And at, at y6, which means x0. So when P is 0, it'll go down like this. But when P is, for example, right there, somewhere near the very tip of the curve, or the vertex point, you will have a tangent to the curve that goes somewhere like this. Okay? So one thing to be understood here is that the tangent at this point will have a certain value for the y-intercept for that line that depends upon what the x value of P is. So if we increase it, for example, then the y-intercept of that tangent line becomes somewhere down here, right? But if it's at 0, then the y-intercept of this curve at this point is equal to 6, right? But the gradient is different. So step 1 would be we can define a function for the gradient. We can say m of x, right? So the gradient at a certain x value, in this case later on we're going to plug P in position of x, and that's what our calculation is going to be. But for now, let's just perform differentiation on this here quadratic. So 2 times 3, so we're going to multiply the power with the coefficient and then subtract 1 from the power. So we're going to say 2 times 3, which becomes 6. Then we're going to place x as is, and then 2 minus 1. So that's to the power of 1. Okay? And then over here, we're going to say minus, and then we're going to do the same for this as well. For the second value, which is 5 times x to the power of 1. So we're going to say 1 times 5 is 5. And then x to the power of 1 minus 1, which is 0. So that becomes 1. So 5 times 1, which makes 5. And then for plus 6 in differentiation, I myself don't know the reasons why, but we typically tend to remove the alone constants, the ones without a variable, right? So yeah, any coefficient is where this rule will apply, and then we just remove this. Essentially, this just means plus 0, but we don't need to write it because it doesn't matter. So we have our function for our gradient. We don't need this to the power of 1 because, well, it just is how it is. You know, anything to the power of 1 is that number itself. And now we can see that this gradient is this is a line that is being shown. We should hide this for now because we don't want to see the gradient of this. So the next step would be to determine the c value that is dependent on the x value of p. So we're going to define another function called c at a certain x value equals to, and so how do we normally have c in a line? We have y equals to mx plus c. F of x, so let's just like write this down for a reference. F of x equals to mx plus c, right? So if we solve for c, or also we can also phrase that as we make c the subject, we can move this mx on the other side, and what we get is fx minus mx, right? So this is equal to c. So we can define the function of c of x as f at a certain x value minus m, so the gradient at a certain x value, times x. And that is it. That is our c function. So we can get rid of this now, and we can hide this as well. We don't need it. So notice how, or I guess if we do this, yeah. So we can hide this as well. Let's move this down here. Down here. Perfect. Or up here. Yeah, okay. So now that's easier to read, and we have made a function that gets the gradient at a certain point. So a gradient at when p is 0, right? And there would be some, it'd be going downwards, so it'd be more steep, and then the gradient would get less and less steep as it approaches the vertex point, or the tip of this curve. Yes? So at this tip, it's going to be 0, which is going to be as not steep as it can get, if you will. So yeah, the gradient changes depending on what the x value is, and the value of c would also change depending on what the x value is. So the value of c depends on the gradient and the y value, as you would see later that it touches. So let's say there was a gradient over here, it would touch 6, right? It would touch this particular coordinate, 0, 6. But it won't intersect at 2 positions. It will only touch it once, and then it will have that particular gradient at this point. So for example, let's say we plug in, 0 into this, into m of x, right? So 6 times 0, 0 minus 5. So the gradient is, it goes downwards by 5. So you can see how roughly it maps almost perfectly. I am showing it with my mouse, but later on I'm going to display this as well, and you'll be able to see what I'm trying to demonstrate here, that this is going to go down by -5. And this is, now that we have our 3 functions, what we can do is we can make a line. So we'll make a line, right? And we'll say m at p times x, so the gradient at p times x, plus whatever the c value is at p. And you can see how, you see wherever p is, that this tangent touches the curve. So we can change this, and you can see how this tangent wraps around the entire thing. And now we'll prove my point of the tangent, or the gradient of the tangent at 0, 6 being -5. So we can go when p is 0, right? So when the x value is 0, the gradient becomes, it goes down by 5. So 1, 2, 3, 4, 5. And if we look here, you can notice that it perfectly crosses the 5th box. So I was correct. Now, as you can see, this tip, this vertex point is 0. The x value at the vertex point is 0.833. Obviously, the y value is dependent on that value. So we can just say 0.833 yields 3.917. So the gradient at 0.833 is some value times x plus c of 0.833, which will yield the c value at 0.833, which in this case is 0. But it'll say that y at that point, so y at that point, which is 917, when you plug it into f of x, minus the gradient at that point times x, so you get the c value. And hopefully now it is clear how you can model a tangent wrapping around a curve on Desmos. Thank you everybody for watching.